Hello. Let's talk about really solving some torque types of problems. Right? Here we have a 5 meter long rod. There's its mass. It's in equilibrium. And the only reason it's in equilibrium is because of some force F that's applied at its left end. Now, why must there be a force applied at its left end there? Well, here's kind of the big reason. It has to do with this. And it has to do with the practice of drawing a good free body diagram. All right, here's our object. And we should really draw all the forces acting on it. One of them is that force F they talk about. Well, what else? One is its weight. That we always assume, because we've seen some evidence for it, that gravitational forces act at center of mass. This is a nice, what we call uniform object, a rod, where there's just as much stuff over here as there is over here. So, yeah, gravitational force acts, in this case, right in the middle. Okay, so why do we have to apply a force F there? If we didn't, and this really is where this system will rotate. So if we look at an axis of rotation there, well, if there were no other force, mg would tend to make the system rotate that way. Well, why doesn't it? Well, it doesn't because we apply a force F here that would tend to make the system rotate that way, and those are opposite rotational directions. Okay, so that's why force F has to point down. All right, now let's not forget, of course, about this normal force that's exerted right there, all right, due to the contacts with that fluid. Now we want to find in A the normal force. All right, so, well, there's a few options here. I'm first of all going to erase this little indicator for axis of rotation. And here's why. Well, first of all, let's talk about this. All right, static equilibrium. This means for us now two things. Right, for a long time, several weeks, it's meant that net force acting on an object is zero. As some of you now know, it also means that the net torque acting on an object is zero. And in any good problem, you're going to have to apply both of these principles or conditions. All right? And so let's start, let's start arbitrarily with a net force statement. That happens to be in the y direction. So this just says that normal minus mg minus that force F is zero, or that the normal force is mg plus F. Nothing fancy there. That's simpler than most net force statements that we've written. Right, so fine. Now look at the problem. The problem is, if we want the normal force, we have to know what force F is, and we don't know what force F is. So bottom line is, right now, if we only looked at a net force analysis, we'd be out of luck. There's no way to find two unknowns in the same equation with only one equation. So what we have to do is a net torque analysis. And here's the deal. If we're looking for normal force, well, what it makes sense to do, or what you really have to do, is choose an axis of rotation that gets rid of, in this case, one of the unknown forces. Now, we want to find normal force, so we actually can't put the axis of rotation right there at the normal force, or where it acts, because then it wouldn't produce any torque about that axis. So what we do is we say, well, let's assume a hypothetical axis of rotation at that left end where the force F acts. Because if we choose the axis there, then force F creates no torque. Now some of you are saying, but the thing rotates at the fulcrum. It doesn't rotate at the left end. But that's okay. All right? Because if net torque is going to be zero, as we talked about in class, that means that net torque about, I really should say every, I'll leave any, that's fine. Any and every axis has to be zero. It doesn't matter where we choose an axis net torque is going to come out to be 0. Okay? So, here's what we have now. Well, about that axis, we still have this mg that makes, or would tend to make the rod rotate that way. But n would tend to make the rod rotate this way, and those are opposite rotational directions. So we can write a net torque statement arbitrarily if I choose that to be the positive rotational direction. Well, I would say that the torque created by the normal minus the torque created by mg equals 0, or those two torques are equal and opposite. That's an N, by the way. Okay. Now, the long way of doing this is saying, well, R to N times N equals R to mg times mg. All right, so I might even just do this now, that normal is R to mg times mg divided by R to N. So normal is R to mg. Okay, so R to mg is that. From the axis of rotation to the point of action of the force. I mean, really, R of mg is right here, but I can just move that vector downward. It's still the same vector. All right, how far is that? Well, that's 2.5 meters. How do I know? Well, because the rod's 5 meters long. So 2.5 meters. mg, 12 kilograms. Well, that's 120 newtons of mg. Yeah, good, good. And let's see, R to N, well, that goes here to here. There's R to N. And, well, if this is 3.5 meters, then R to N has to be 1.5 meters. The whole thing is 5 meters long, right? There's 3.5 meters there on the right of the fulcrum. There's 1.5 meters on the left of the fulcrum. All right, so we have enough to calculate M. Excuse me, N. 2.5 times 120 divided by 1.5 equals 200 newtons. Okay? And now, well, we could do another net torque analysis around any other axis, really, because there's now only one unknown. But what you can do instead is just take this and pipe it into there, and we can rearrange this. And, well, now we want to know F, so we can say it's N minus mg. Or it's 200 minus 120, so it's 80 newtons. What do you think? Fair enough. So like I said before, in any good problem, you're always going to have to do both the net force analysis and the net torque analysis. Fair enough? All right, let's look at another. Uh-oh. Look at this crazy thing. Semicircular sign with a 1 meter diameter and a weight W is supported by 2 wires. There's one, there's the other. What's the tension in each? All right, so here's where I want to point out the value of some terminology and how we use that terminology. So let's look at some forces, right? Well, hopefully, clearly, you got a, let's call that a T1, you got a T2. Now, those actually are not the same size. We'll show you that when our analysis comes through. And then the mg, well, that acts at the center of mass. Now, where's the center of mass of this semicircular thing? It's actually not like halfway down here. There's a calculus derivation. Let's say it's around there. Okay? And that's where we can say mg acts. Okay? And so, well, I mean, hopefully pretty clearly, if we use a net force equals 0. That just says that T1 plus T2 equals, oh, you know what? Let's not call it mg because it just says it has a weight W. So let's just say T1 plus T2 equals W. And what we're going to end up doing is finding T1 and T2 in terms of W. We'll say how much of the weight does each one hold up. But they're both unknowns. T1 and T2 are unknowns. We're at a dead end as far as that goes. So here's what we got to do. We got to go to our net torque. And what we have to do is choose an axis such that we can eliminate the torque created by one of our unknown forces. So what I'll do is do this and say, what if we chose an axis there? All right. All right. So that means, well, I'm going to just recommend don't draw this. Harry, don't draw. R for W looks like that. It could look like that. Except notice that now, well, our real sort of formal expression for torque was that torque is R times F perpendicular. So we'd actually then have to find the component of W that's perpendicular to R. But I don't even know where this is. You know, how far, so what's this angle? I don't know. So here's a really nice luxury with doing torque stuff. And that luxury lives in the terminology about what R really is. All right, so R, remember, where am I going to write this? R is a vector from an axis of rotation to a point or a line of action of a force. The point or line of action. Well, here's the point of action. But we can also define this line of action of that force W. And so here's the beauty of this. Is we can draw this vector R, and the great thing about it is, well, W is perpendicular to that R. All right? So we actually just need to use that R. Now notice, before, don't draw this, before we used a longer R, but then we had to break W up into components and use a smaller W. This component of W is smaller than W. Right? But now, instead of that, what we're doing is we're saying, well, let's take the whole force W, but use this smaller R. So this is actually, you can actually call this, I mean, while it certainly is, well, I'm going to call it this, RW perpendicular. It's the component of R that's perpendicular to W. We've talked about, right, using, well, the component of force that's perpendicular to R, but you can also use the component of R that's perpendicular to the force. It doesn't matter which combination you use. You're either using the whole R and part of F, or the whole F and part of R. Okay? So that's how we're going to do it. We're going to write our net torque statement as the following. Let's see. So we got a torque created by W that would make the system rotate that way. We got a torque from T2 that would make the system rotate that way. Those are opposite directions. So we can arbitrarily assign a positive direction and say that the torque from W minus the torque from T2 equals 0, or sure, torque from W equals torque from T2. And then this is R to W, or really R perpendicular to, RW perpendicular we called it over there, times the whole force equals R to T2 times the whole force T2. Let me. Oh gosh. Okay, so let's see. R to R perpendicular to W. I'm actually going to call that half the diameter times W. And R to T2 is 3/4 of the diameter times T2. Yes? You understand? I mean, I guess why bother using numbers? Sometimes fractions can be easier. It's nothing wrong with saying 0.5 and 0.75, all right? But you notice here these D's can cancel. Not that D. It's not even a D. Yeah, these D's can cancel. And we get that T2 is, let's see, times 4 divided by 3. So that's 2/3 of W. Am I right? 8 over 4 over 6. Yep. 2/3. So T2 holds up 2/3 of the weight. And what does T1 do? Well, if we look over here, we get that, well, T1 is W minus T2. Why do you keep writing it up there? Minus T2. Sure. And so T1 is, well, W minus 2/3 of W. It's 1/3 of W. Of course it is. If T2 holds up 2/3, then T1 holds up the other third. All right. So what ends up making it not tricky is your ability to do something kind of tricky, which is to just use part of R. All right. All right. So, yeah, there's a couple of situations when things point when there's angles involved, right? And a couple different ways of addressing those situations. One of which we just kind of looked at, but I want to talk about them explicitly. And so here we have, like a pole here, and like a plank here, and there's a wire here that holds up the plank, right? And then some physical connection, at least the plank's pressed up against the pole or something like that. All right, and so what we have, let's see, what torque does the wire's tension produce about an axis located at the wall? So it's just telling us, put the axis there. And all this is saying is, if there's a tension force that looks like this, how much torque does it produce? Well, since there's this angle involved, one way to look at torque is use the whole R and then use a component of F that's perpendicular to that R. All right, so, let's assume that they told us this angle theta. All right, well, here is the whole R. Here is what we call T perpendicular. And again, this is angle theta. And so angle theta, well, sorry, yeah, T perpendicular really could be over here in this little triangle, which the angle's not staying home like I wanted to. But what we end up with here is, well, torque is R times T, well, F perpendicular, or in this case, it's R times T perpendicular, a little bit redundant. And we could call that R times, well, that would be T sine theta. All right, so, I mean, that's it for this problem. There's no, oh yeah, we do have, oh yeah, look, 25 degrees. We do have enough to actually to solve this problem. Well, actually, we don't have enough to solve this problem because we don't know how long the plank is. But what I'm really focused most on here is that in this case, it would be appropriate to express the torque created by tension T like that. The whole R from the axis to where T acts times the component of the tension that's responsible for the tendency to make this object rotate. All right, that happens to be T sine theta. Okay? Here's a different case where, well, we're going to do it the other way, and we're saying this is about, well, let's apply a force right here. This is like a domino or something, and this thing, the question is how much force is required before this object just starts to tip over. All right, well, if it's just going to start to tip over, it would rotate about that axis. Agreed? All right, so, if we want to do this, when it just starts to tip over, here's what we have. We've got, this is kind of, we should really say like just before it starts to tip, so this thing is still in equilibrium, all right? And we could say that basically there's a torque created by this force F, but in this case, there's, well, don't draw this. There's the whole R that looks like that, all right? And then there's this component of F that's perpendicular to that, and based on the dimensions of this domino, like we'll call this its height, and let's call this its width. We could write like an expression for this angle, like the inverse tangent of blah 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 blah. But instead of that, instead of using that whole R and part of the F, here's what we can do. In this case, it's a lot more convenient to say, well, here's that line of action of this force, and here's a vector R that's perpendicular to that. So in this case, because it's just plain old easier, we can say that torque is R perpendicular times F. And so the torque required by that force F is just F times the height. Now, I understand we're not actually answering this question, how much force would be required. Well, what you'd actually do here is there's this other force, mg, that acts like that. And again, so if this green one is R perpendicular, or maybe we call it RF perpendicular. Well, look at this. Here's little tiny R mg perpendicular. Right? We're still calling this width W. So notice that the mg force would make the system rotate this way about this axis, and the F force would make it rotate this way, and those are opposite directions. So you could actually say that the torque produced by F equals the torque produced by mg just before it starts to tip over. Well, the torque required or produced by F, we said, is the whole F times h. And the torque produced by mg, well, it's R mg perpendicular, which happens to be W over 2 times the whole force, mg. All right, so sometimes it's just way easier than dealing with, breaking lots of things breaking things into components and even using angles at all. Sometimes you can just say, well, where's the shortest part of R that's perpendicular to the force? Okay? Okay, here's another very standard kind of question. And let's see, we got a floodlight in a park. It's supported at the end of a beam of negligible mass, hinged to a pole. There's the angle. find the tension of the cable. Okay, so here's, we got this beam of negligible mass. Negligible mass. So what we do have, forces acting on this beam are this tension, and this M, I'm going to call it M light G. And now there has to be a normal force here. How come? Well, look, the tension pushes the thing this way. There's got to be a force back to the right. And then, you know, we don't know that this upward component of T and this weight of the light thing are the same thing. So let's say, I don't know, let's say that maybe there's another force. I'm going to also call it another normal force. It comes from contact between this beam and a hinge. So I'm going to call this Nx and I'm going to call this Ny. Fair enough? Now we don't have to do this, the mass of the beam, because we said a beam of negligible mass. All right, so a net force statement, well, we actually need two of them. I'm going to do this. I'm going to call this T perpendicular, and I'm going to call this T parallel. So a net force in the x direction equals 0. Well, that means that Nx equals T parallel. Agreed? And if this is theta, which it is, 30 degrees with the beam, that means that Nx is T cosine theta. Fair enough? Well, two unknowns. Sorry, out of luck. Okay, so let's do a net force in the y. And that's going to be that Ny plus T perpendicular equals M light G. And, well, there's two unknowns there. All right. All right, so now what we have to do is a net torque. Now, we want to do it, we want to pick an axis such that we can eliminate some unknown stuff, right? And boom, a-doom, doom. If we do it here, we can eliminate two of those. We can eliminate any potential torques by Nx and Ny because they act right at the axis. So the two torques about that axis are this torque from T perpendicular and this torque from Mg, which are in opposite rotational directions, and therefore arbitrarily, well, it doesn't matter what sign you assign. We can say the torque from T perpendicular equals the torque from Mg. And, well, let's see. If this beam has a length L, and this is L, T perpendicular equals L, M, G. Oh, look at that. It says that, well, that's gone and that's gone. Or it says we just found T. It's mg divided by sine theta. Mg we're given as 200 newtons divided by sine 30. Oops. Oh, duh. So T is 400 newtons. Now, if you didn't notice, this says that this is 200 newtons. Well, it also just said that mg and t sine theta, which is t perpendicular, are the same thing. This is also 200 newtons, which actually means that ny ain't even there. It's 0. Follow that? Not only have we found T, we've also found out that if these two forces are the same, and, well, this is the only downward force, then that means this is the only upward force, and, well, this just plain old isn't here. There is no upward force or downward force at that hinged end. All right, but what we can do now is use our value of T in here and say that Nx is T cosine theta, or 400 newtons times the cosine of 30 degrees, and Nx is 346. Okay? All right, so you'll find some opportunities very soon to solve problems where you will need net torque statements and net force statements, perhaps both in the x and y direction. You'll find opportunities to calculate or find torques using components of forces that are perpendicular to some r, or by using components of r that are perpendicular to forces. All right? So, this is a little bit long. I'm sure some questions will arise tomorrow, but I'll look forward to that. Okay? See you, folks.